Hello everyone, I'm Shaurya and I will present our work, ExtMem, which is a collaboration with my colleagues at UBC, but specifically want to highlight that Sepehr, the first author, is a graduating master student going to the industry job market. Now, let me tell you something that you've probably never heard before, definitely not at this conference or the current session. Memory is expensive. Google reported that memory is a bottleneck for data centers, and Meta has reported that the cost of DRAM is about 30% of a total data center cost. That is very high. That is very high, and efficient usage of DRAM is paramount. Well, okay, but what about the applications? Well, they aren't making our jobs any easier. Applications are memory hungry, and we have larger graphs to process, bigger machine learning models to train, and presentations to fix, and bigger databases to query. On top of that, different applications have different kind of memory usage patterns, which makes our jobs even worse. To reduce memory consumptions, data center operators rely on many different techniques and setups. Memory tiering over CXL is one of the approaches where you use a DRAM pool to store application data. Another technique is to use memory disaggregation, where memory is offloaded to SSD or over RDMA. Another option is to use accelerators, such as processing in memory, which have totally different performance and energy characteristics. And one thing that is clear to me is that memory management policies need to be tailored to specific hardware and applications running on top of the hardware. So the overarching problem is that the current kernel memory management policies are insufficient to deal with all these scenarios, and they are inflexible. If you want to go to user space, current frameworks have a large overhead. And in the rapidly changing environment I just discussed, there is a need to support new scenarios, but development inside the kernel is really hard. One prior work has reported changing 20 files just to implement a prefetcher. So our claim is that we need a solution that makes it easy to develop policies while maintaining performance. To solve this problem, we propose ExtMem. ExtMem is a flexible framework that allows users to easily build memory management policies while having high performance. It is inspired by semi-microkernel approaches and runs in user space on top of Linux. It is compatible with existing applications and is dynamically linked with applications similar to library operating systems. ExtMem has three components, the first one being the core layer that is responsible for managing the memory state and communicating with the kernel. The second layer, the observability layer, is responsible for collecting data for whatever users need to implement their policies. And the policy layer exposes an API to users to implement eviction and prefetching policies. I'll discuss the design of these components, but please check out the paper for implementation details. So the core layer maintains data structures and states, such as struct page or what pages have been swapped out to disk, etc., and whatever other information that ExtMem needs. Whenever the application makes a memory system call, such as mmap to allocate new memory, ExtMem will transparently intercept this call and update any data structures that you need for bookkeeping and do other processing, and forwards the interception to Linux. One of the key challenges for ExtMem is communicating page faults from the kernel to the framework. And prior works have used an existing technique called user fault FD in the Linux kernel to do this. However, we observed that user fault FD doesn't scale due to expensive IPC and synchronization. Let me give you a primer on that. So the user fault FD runs in a handler thread, and the handler thread polls a fault descriptor inside the kernel. Once the application experiences a page fault, Linux writes to the fault descriptor that user fault FD is polling on, and once the user fault FD handler sees that there is a fault, it will do whatever processing it needs, does a syscall back to Linux, and then Linux finally goes back to the application, and application can continue execution. As you can see, there's a lot of unnecessary IPC and serialization at the handling thread, which limits the performance that user fault FD-based systems can have. ExtMem instead uses an upcall-based approach, Whenever the application experiences a page fault, the fault is forwarded to the core layer on the same thread. The core then processes the fault, maybe it reads a page back from disk, and then once the core is done processing the fault, it returns to the kernel, and fault thread resumes normal execution on the same thread. Thus, ExtMem removes the unnecessary IPCs and removes the serialization that user fault FD experiences. The observability layer of ExtMem interfaces with the kernel and the hardware to get whatever information your programmer might require to write custom policies. Currently, we have specifically these particular data. We have page fault addresses, accessed and dirty bits from page tables, and we support hardware counters such as PEBs, but additional data collection features can be easily added for future systems such as CXL. The policy layer implements a simple API similar to prior work, where a user can implement eviction and prefetching policies. In order to show the effectiveness of our framework, we implemented 2 policies in ExtMem. We replicated the 2QLRU policy from Linux in about 300 lines of code, whereas Linux implements it in about 500 lines of code spread across multiple files. And we also implemented a simple virtual memory prefetcher in about 200 lines of code. To evaluate ExtMem, we ran multiple applications, and we specifically answer the following questions. Is ExtMem's upcall method any better than user fault FD? Is the overhead of ExtMem reasonable? Are ExtMem's policies functionally equivalent to Linux? And can we actually improve application performance using ExtMem? For the remainder of this talk, I will just focus on the first and the fourth one, but there are more results in the paper. To understand how ExtMem's upcall compares to user fault FD, we ran 2 experiments. In the first experiment, we measured the latency of servicing page faults for a micro benchmark, and we found that ExtMem's upcall framework has a much lower latency than user fault FD. This is because of elimination of complicated IPCs and scheduling that user fault FD requires. In the second experiment, we measured the scalability of these approaches for handling concurrent page faults. And our micro benchmark basically runs a lot of threads that all of them experience page faults. So in this graph, lower is better. And as you can see towards the very bottom of the graph, kernel is obviously the best one. But ExtMem scales almost as well as the kernel does, whereas user fault FD, because of its expensive serialization, does not scale when it comes to concurrent page faults. These 2 factors combined give ExtMem the performance that it can get. To understand if we can improve application performance, we did a case study on PageRank. PageRank essentially works on 2 arrays, a vertex array, which is mostly hot and small, and an edge array, which is larger, and once it's used, it's never used again. Using this intuition, we designed a very simple custom policy for our eviction, which is to never swap out the vertex array, and to discard the edge array as soon as it is accessed. And we build a prefetcher that prefetches the window of edge arrays that will be used in the future. We ran our custom policy on the gap benchmark suite using the Twitter dataset and allowing 50% of memory fitting in DRAM. What we found was ExtMem's 2QLRU, which is the Linux equivalent of implementation, performs similar to Linux, but ExtMem's specialized policies, which is ExtMem PR, performs much better than Linux. Surprisingly, it's only 2x worse than 100% data being in memory. To conclude, ExtMem is a flexible, high-performance user space framework for implementing memory management policies on top of Linux. ExtMem effectively eliminates the overheads associated with past approaches, such as user fault FD, and empowers users to harness the performance advantages of application-aware memory management. The code is open source, and again, I would like to point out this is Sepehr's master's thesis, and he's graduating and he's looking for industry options. So if you're looking for an exceptional kernel developer, please contact Sepehr. That is his QR code. Thank you, and I'm happy to answer any questions.
Thank you.